Good afternoon, professors. We are Team 90068, and our research topic is spherical Fagnano's problem and its extension. Fagnano's problem is to determine the inscribed triangle with minimum parameter of a given acute triangle. The answer is the Orphic triangle, and its general problem has been solved. Inspired by this problem, our group is curious about the situation when this general problem is discussed on a sphere. That's why we work on this problem. In our paper, the first chapter is to introduce some fundamental spherical geometry knowledge, and the next three chapters are our achievements. In the research, we use stereographic projections that is able to project all the points on a two-dimensional plane. As it is conformal, we can use the knowledge of Euclidean geometry. In Chapter 3, we divided the spherical triangles into 4 cases according to the number of obtuse angles. To help solve the problem, we prove a useful lemma, angle-side relationship of spherical triangle. The first case is proved by spherical sign law. The second case is proved by finding the contradiction in Euclidean geometry via stereographic projection. Case 3 and 4 can be proved by supplementary spherical triangle of case 1 and 2. In the case of acute spherical triangle, P is the variable point on BC. We reflect the triangle about great circle AB and AC. We know line P prime P double prime is the parameter of the inscribed triangle. Using spherical cosine law, we prove that P prime P double prime is minimum when AP is perpendicular to BC. By angle tracing and reflection, we further prove that Q and R are the foot of altitude. Hence, Orphic triangle PQR is the solution. Using similar reflection method, we prove the case with one obtuse angle only has degenerated solution. Since twice angle C is larger than pi, C is like a barrier point that P prime P double prime cannot cut AC. So the path is P prime to C and then to P double prime. The parameter of PCR is minimum if it becomes twice the altitude from C to AB. In the case of two obtuse angles, just like the previous one, there exists barrier points B and C, so the path must passes through BC to be minimum. In the case of three obtuse angles, A is a barrier point. There are two possible paths. Applying angle-side relationship, we can deduce that the minimum parameter is the side opposite to the smallest angle. In Chapter 4, we divide the spherical quadrilateral into 5 cases. We first introduce a new definition, expanded form of the spherical polygon. Take quadrilateral as an example. After reflecting the quadrilateral 3 times, the corresponding sides AD and A'D' will intersect at point S and N, forming a two-gon, and we call the sixth set the expanded form. Based on the two-gon, we use differentiation to find the minimum path of P prime P, stated as theorem 4.2. There are 2 cases. In case A, PP prime is minimum when it coincides with AA prime or BB prime. In case B, PP prime is minimum when MP is equal to MP prime or having a degenerated solution AB prime or BA prime. In the case of spherical quadrilateral with 3 acute angles, we prove that the degenerated solution is the spherical triangle passing through the obtuse angle. By considering the expanded form and theorem 4.2, PP prime must pass through C. This is an example on stereographic projection showing the path passing through C. By reflection, we prove minimum path is the spherical triangle CPQ. In the second case, spherical quadrilateral with 2 opposite angles and 2 obtuse angles, we can use the similar approach as the first case to prove the degenerated solution is twice the diagonal passing through the 2 obtuse angles. Again, one example is attached. We know that cyclic quadrilateral in Euclidean type has infinite solution if the center of the circumcircle is lie inside the quadrilateral. However, for spherical cases 3, 4, and 5, there are only degenerated solution even it is a cyclic spherical quadrilateral. Definition of a cyclic spherical quadrilateral is one that can be inscribed in a small circle or great circle. We use stereographic projection to prove that a spherical quadrilateral is cyclic if and only if the sum of the opposite angles are equal. Now consider the expanded form of a cyclic spherical quadrilateral. Using spherical area formula, we calculate the two areas are equal. By theorem 4.2, we cannot determine where point P should approach to. It is also true for almost cyclic spherical quadrilateral. Because of this property, the approach to find the degenerated solution is different to Euclidean. We have used the stereographic projection and distance formula to find three counter-examples respectively. We know that when P is reflected about a great circle tau to Q, then reflection point Q prime is the inversion point of P prime with respect to tau prime, and it is the distance formula on stereographic projection as stated. Here is the counterexample for the cases of two adjacent acute angles and two obtuse angles. We can see even the sum of alpha and gamma is greater, the spherical length of B double prime, B triple prime is smaller. The other two counterexamples also have the same results. Although we cannot determine where P should approach to, we still find an algorithm to find the degenerated solution. For the case 3, with two adjacent acute angles and two obtuse angles, we know that P must pass through either B or C, so we need to divide it into two cases. This is the stereographic projection of this case. If P passes through C, we can find angle theta in terms of alpha and AC, which are given. Since C prime C double prime may lie under or above point P, we find the equation presenting the parameter in each case, so we can calculate the minimum value. Apply the same method for the case start with B and compare them. We can find the minimum degenerated solution. For the case 4, we use the same method to find the minimum parameter in each case and compare them. We find that the degenerated solution may be one of these three. The last case of quadrilateral with four obtuse angles, we prove that the degenerated solution is twice the shorter diagonals. To generalize the solution to n-gon, we find that the result is related to the parity of size of the spherical polygon. First, we defined it and inscribed this spherical polygon is a closed path of light if and only if all the angles of incidence are equal to its angle of the reflection. In the case of spherical polygons with odd number of sides, we considered the expanded form and used the theorem 4.2 to prove it has an inscribed polygon with minimum parameter if and only if it is a closed path of light. For the case of even-side spherical polygon, consider its expanded forms. As P must close to point A or point A to N, only a degenerated solution can be attained. From all the results we got, we know that the solution of cases in spherical triangles will be similar, and in quadrilaterals, the largest difference is that the solution may exist in Euclidean geometry, but on a sphere, there is only degenerated solution. Even the spherical quadrilateral is cyclic. When extended to n-gon, the cases of odd-sided polygon are same. In case of even-sided polygons, only Euclidean polygon has a solution under sufficient condition, that is, the sums of alternate angles are equal. This is the end of our presentation. Thank you.